Hi, today we talk about utility theory. Utility theory is the basis behind estimation theory and Bayesian estimation theory in general. Why is that the case? Because if we look at our Bayesian estimators, especially if we look at our expected loss, given x, this is a number. This means that we can minimize this. That's one thing. The other thing is that we actually order every single one, we are able to order every single one of our decisions. That means if we have delta 1 and delta 2, two different estimators, we immediately know just by evaluating the loss which one we prefer, because either the loss of one is smaller or equal to the other, or the other way around, and that way we know which one is better. This has some heavy consequences. This has drastic consequences. And I'm going to spend the whole of today's video on explaining why. So utility theory is just pretty much what I described with our loss function. Utility theory for us assumes that we have some space R, which we call the reward space, which first of all fulfills axiom 1 that for any two rewards we can order them. So we have an ordering, which I write by this sign, which means we prefer R2 over R1, or we prefer R1 over R2. And this is true for any two elements in the reward space. In estimation theory, no matter what kind of decisions we make, we can compare them. Already, this is not necessarily true. And this is how I'm going to proceed today. I'm going to state one of the axioms. We're going to take a couple of axioms behind utility theory, and I'm going to contrast most of them with a paradox, a situation where this pretty simple, I mean, this is not a heavy it doesn't look like a heavy restriction when you look at it at first, because obviously we have to order things to make a decision. If we don't know if one reward is better than the other, then we can't do estimation theory at all. But I want to contrast them with some situations where, okay, maybe it's not so clear. We're not always in a situation where these axioms hold. So the first one, as I just mentioned, it's very, very commonsensical that in any kind of these situations you just have to be able to compare rewards. Otherwise you can't come to a decision. Unfortunately, it's not that easy. And here I'm just going to list one example of philosophy, which is the trolley problem. Very, 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 very well-known problem. For those of you who don't know, I hope I'm not going to mess this up. So basically the idea behind the trolley problem is you're taking a walk and you see a lever. The lever is for a train. Yes, this is a train. Don't judge my drawing skills. And the trains, it's moving, you can't stop it. And it's not supposed to move because there are workers on its track working, and the train is very fast. You can't. There's no way to cheat. You can't tell the workers to get off the line. The train is going to hit them unless you pull the switch. In this case, the train is going to another track where there's only one guy. And then the dilemma is, should you pull the switch or not? And this is just one example where you can't, well, you can at least make an argument that you can't weight the life of this guy against the lives of the other 2 or 3 people, even though you could argue that they have the same worth. So still major argument of should you pull the lever or not. I'm just going to leave this here. I think for the first axiom there's not that much arguments, but I just wanted to give you one example where it's not that clear. And okay, this looks like, okay, what does this have to do with statistics at all? We're talking about a decision space when we're talking about estimation theory. And this can be any decision we have to make, and this includes very heavy and difficult decisions, like the decision in the trolley problem. So, okay, we didn't need a statistic right now. We don't have an estimation problem, but we could still have to make difficult decisions given our estimation. Nevertheless, A1 is pretty reasonable under normal circumstances. Another very reasonable and necessary assumption is A2, which rules out circularity. A2 is the assumption of transitivity. Namely, if we have the case that R2 is preferable to R1 and R3 is preferable to R2, then this has to imply that R3 is preferable to R1. We have to make these assumptions, otherwise we get into some rock paper scissors scenario where R1 is better than R2 is better than R3 is better than R1, and now somebody asks you to choose one of these 3 rewards, but how can you choose? None of these is optimal. In fact, every one's better than the other. We have to make these assumptions. However, that doesn't mean that it is the case. Again, this looks like a crazy, at first it looks like a crazy idea that this doesn't make sense, or that there even is a situation where this doesn't make sense. But there famously is, namely, I'm going to mispronounce his name, the Condorcet Paradox observes this phenomenon in voting. Let's say we are a very tiny vote. We have 3 people, 1, 2, and 3, and 3 parties. Person 1 votes for party A, but we are allowed to list our preferences. So person 1 lists party A as his first preference, but he lists party B as his second and party C as his third. Person 2 strongly prefers party B, but as his second preferences 2 chooses C, and as the third S is third, 2 chooses A. And then 3 does something similar, C, A, B. This already gives us a situation of where no transitivity is in this situation. Why? Well, let's look at party A and party B. Which one's better? Well, 1 wants A, so 1 would choose A over B. 2 chooses B over A, so we give it the minus. And 3 would actually like to have C, but that's not an option. And as his second preferences, he has A. B is the third. He really doesn't like B. So A wins in this encounter. The same thing happens when we compare B to C. B is better than C. Why? Because person 2 really wants B to win. 1 has B as the second choice, and 3 really doesn't want B to happen. So B wins against C, and then same argument, C wins against A. This is a paradox very well known in voting, that we can't, the way we pick the party depends heavily on the system. So if we have a system where we first choose the party, where we first have, like in France, where we first get to choose between very many different parties, and then we have a knockout round between the 2 largest parties, we're going to have a different result, even though the votes are the same, than for a system where we just pick the party with the largest number of votes in the first round. And in fact, there's no decision rule which, there's no voting system which makes everybody happy, basically. That's what this paradox says. Because you very much like to have this kind of voting system, but it just doesn't exist. So this is a situation where we don't have transitivity, but we want transitivity. We have to have it if we want to make any kind of decision. Moving on to an extension to our reward space. By the way, I should be mentioning, okay, why am I talking about axioms and utility theory and so on? We're going to see how basically we want to construct, we want to see how we got to this call of a loss function. Given that we make the most basic commonsensical assumptions, so far we've only assumed that our that there's some outcomes of the experiment, some decisions which we prefer over others, and that there's no circularity in our arguments. So these are very, 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 very small, although as we've seen, not obvious, but very small assumptions. So we want to make the smallest assumptions possible in our system to see when we get, under which conditions we get this loss function, under which condition we can order space the way we ordered it under Bayesian estimation theory. And this tells us something about the requirements, which as it turned out are going to be pretty heavy requirements in our system. So how did we get to L given our axioms? That's the question I'm trying to answer. Should have probably said that at the start and not in the middle of the video. Anyway, so for the next axioms, we need to expand our space a little bit. So for A1 and A2, we talked about R, which is the reward space, which is the space of the decisions that we can make. The reward space is just a space, and it's not random. There's no random component to it. So we're going to add that. we're going to expand R to P. P we're going to define as the space of random rewards. Why do we care about random rewards? This can happen pretty easily. For example, actually most rewards are random. For example, instead of getting your money in cash, which is also kind of random because the value of money changes, you could get an asset in the stock market. And the value of your assets are highly random, highly depend on outcomes which you don't know much about. So that's one way they could be random. And another, as I mentioned, is just the value changing. That you don't necessarily know what value the reward's going to have. Now we are looking at, unless I stated otherwise, we're looking at random variables. So if we look at any reward R, we're talking about a random variable. This has an interesting consequence that P is convex. And that's very, very useful. So why is P convex? We define the convex combinations of two rewards. Now they can be random variables as we get R1 with probability alpha and R2 with probability 1 minus alpha. And alpha is just some number between 0 and 1. So this is really cool because for any two rewards, we can express mixtures between these rewards. For example, if you have the reward of 10,000 euro and then a reward of 50,000 euro, one convex combination would be, okay, you have a 10% chance or 1% chance of winning 10,000 euro in this game, and you have a 99% chance of winning 50,000 euros. And this is going to have a really, really, really nice consequence, which I'm going to explain very soon. Actually, I can draw it. I can try drawing it. If you just have, this is not an actual coordinate system, it's more like a ranking. If you look at the reward space here, I'm going to interpret the y-axis as meaning if we have R1 and R2 here, they're not actually any numerical values, but R2 is preferable over R1 because it's higher on the y-axis. That's what the y-axis means. So if we have R1 and R2, and we have some R3, which is between those, so R2 is preferable over R3, but R3 is preferable over R1. We can do a really cool trick. So first of all, our space is convex. So actually the line between R1 and R2, every single one of these elements is also a reward, because that's what convex means, that the line between 2 points is still in the space. And now we just take the point which is at the same value as R3, so that's going to be alpha R1 plus 1 minus alpha R2 for some alpha. And this point is the same as R3, basically. What do I mean by the same? I just mean that, so this sign, basically smaller or equal, although we don't mean smaller or equal, we mean preferable, and larger or equal, so none is better than the other. They're on the same level. And this is a consequence of two axioms. First one is that we're indifferent under additional options. So if we have R1 and R2, and R2 is preferable over R1, and we add another reward, nothing changes. So as you can see, I just added some reward on these two sides. I know that here's a drawing where R3 is between these two. R3 doesn't have to be between these two, it can be any value. No matter what value we add here, we still have smaller or equal. We still have that R2 is preferable over R1. And this, if you first look at it, it makes sense. The fact that there can be some alternative which could happen shouldn't stop us from comparing these results the same way we compared them before. For example, if I prefer R2 over R1, but there's some probability that I don't even have the option to choose between these two, some probability that the whole market collapses, for example, which would be, then R3 would be a very, very bad alternative. That doesn't change anything, basically. I can still say that I would prefer R2 over R1, even though it could happen that both of them don't happen. That being said, that's not necessarily the case. I start again with the third paradox. The Allais paradox. You have two choices. First, you have to choose between A1, which says you get 10,000 euros with 100% probability, or A2, which says you get 10,000 euros with a probability of 89%, or 50,000 with a probability of 10%. And then there's a 1% probability that you get nothing. Okay, most people in this situation, so first of all, think about what you would think, what you would take. Most people in this situation choose A1 over A2. Doesn't mean that it's right, but that's what most people choose. Now we have another question. Would you rather get 10,000 euros with a probability of 11%? That's A3. Or would you get A4, which is 50,000 with a probability of 10%? Here again, most people, they choose A4 over A3. However, notice that this is not compatible with our assumption A3. Because I can just subtract the 10,000 times 89% on both sides and get the same problem. So what happened here? Basically, one way to think about this is that we liked, if we chose that, I would choose both of these options exactly the same way that the majority chooses them. We liked the fact that the 10,000 is fixed, it's certain. We're certain that we're getting this amount. And even though the chance of 1% of losing here is very, very small, we do not like the fact that these two, they don't add up to 100%. If this is to, if 1% is fine for you, I mean, we can change the numbers to get something like 5%. It will be a similar paradox. And then when we go down 11%, we're already, both 11% and 10%, they're pretty uncertain. So if we're uncertain, we might as well choose the option which maximizes our expected value, which in this case is 50,000 times 10%. Because that has an expected value of 5,000, which is better than an expected value of 110, which we get for the other option. Yeah, so there's an intuition behind this, and you could argue that it makes sense. However, it's not compatible with A3, because under A3 we can choose, it's fine to choose A1 over A2, but then if we choose A1 over A2, we have to be consequent in our decision and also say we choose A3 over A4. Same way, A2 over A1 and A4 over A3 is fine, but combining these two in this way makes no sense under A3. The other assumption, A4, is very similar. It's in the same spirit as A3. It says that for any R1, R2 and R3 where we have the case that R3 is between R1 and R2 and R2 is strictly better than R1. So this means that they're not equal, but R2 is better than R1. We can approximate R3 in some sense. We can say that there exists alpha and beta such that alpha times R1 plus 1 minus alpha R2 is smaller or equal to R3, and R3 is smaller or equal to beta R1 plus 1 minus beta R2. How is this possible? Why does this make sense? We're just saying that we can choose this constant here so large that we are very, very similar to R1 and therefore we are worse than R3. And we can choose this constant here so small and thereby this constant here so large that we're better than R3. This doesn't mean that our choice has to be linear in some sense. We can say that 1 minus beta is very, very large, something like 99.99%. That's fine. We're just saying that alpha and beta exist. Because then we can have this picture, which I'm going to draw again. Where we can take any value between R1 and R2, even any random value, and just approximate it by a convex combination. So anything, the intersection between those two lines, there will be some reward that's equivalent. And that's the lemma that I'm just going to state but not going to prove. There exists exactly one alpha, so in the above situation, such that alpha R1 plus 1 minus alpha R2 is equal to R3. So they have the same meaning to us, basically. This is very, very nice, because under these assumptions, we can immediately construct a utility function. A utility function is given by u of r. So for any r between those two, we're just going to take this constant that combines them. So this is just going to be not alpha, but 1 minus alpha. When we take any r and put it in this situation where we can apply the lemma, we just take the constant, and this is exactly how we define a utility function. So now instead of having to deal with the reward space, we can just insert any reward in the utility function and get a number. And that's very, very useful. That being said, I didn't even define the utility function. What is a utility function? It's the opposite of the loss function. It's defined by, let's not call them R1 or R2, let's say R3 and R4. U of R3 smaller or equal to U of R4 if and only if we prefer R4 over R3. Note that that's the exact opposite of a loss function. So in a loss function we would have same thing but reversed. In fact, we just get a loss function by taking the negative of a utility function. A utility function has as a domain the reward space, so no random variables, just the reward space, and it maps the reward space onto the real number line. So this here is it's an actual small or equal sign. Why do we care about this? With a utility function, we can simplify our calculations, because we can just take the expectation of a utility function. This is going to be our last axiom, because we can't force this. We don't naturally have this situation, but in probability we often want to maximize expected values. And so our condition is going to be, if we have the situation above, and R3 is actually a random variable, we have that the expectation of the utility of R3 is equal to the expectation of this equivalent value on this line. So for this particular alpha from this lemma, we have the same expectation. So we have that the utility is stable under expectation. And note that all of these are constant, so this is actually just, we can just remove the expectation, because nothing's random in this expression. So under this assumption, I'm going to state a paradox about this assumption as well soon, but under this assumption, we have this really nice theorem that says the expectation of U of R3 smaller or equal to the expectation of U of R4 if and only if we prefer R4 over R3. And we can prove this easily. We just look at R3 and R4, which could be random. And we know that this is the case if and only if alpha. So now again we take this alpha from this lemma. Say this is alpha 1. For this we have to have that both of these are some values between R1 and R2. So for our particular case we have this slightly simple case where we just have some R1 and R2 which actually span the whole thing. Every value is between R1 and R2. So we're going to demand that we have a reward, a best possible reward and a worst possible reward, which is not always the case. But we're just going to demand it because that makes the theory a lot easier. In general, you can generalize this, for example, to finite expectations, which is what we're going to, in the case that we're usually going to have for Bayesian estimators. Anyway, this is the case if and only if we have our lemma. But then we're done, because this is the case if and only if this variable here, which indicates the higher value, R2, is larger or equal to the other variable. And this is just the utility. So that's how we climb the steps. This is the utility, and then we can take the expectation of the utility, and then we're done. This gives a reason for why utility functions are useful. Now let's mention a paradox for why utility functions don't work. Very, very well-known paradox. Let's say you get a bet, you play against someone, he tosses a coin, and he tells you, if I toss head on the first try, I'm paying you €1. If I'm tossing tails, I'm gonna repeat the coin toss. If I get a head on the second try, I'm paying you double the amount. And so on. For the third try, you get €4. And for the cave try, for any cave, doesn't matter how long I take, you get 2 to the power of k minus 1 euros, which is a lot. And you can think about, okay, we want to make this game fair, you should pay something for the game. What is the amount that you should pay? Now you can calculate the expectation of this game. So let's say this is x is our earnings. You can calculate the expected value and you get, well, 1 is the first try and the probability of winning it is 1/2, plus 2 is our second try, probability of winning it is 1/4, so we have 2 times 1/4, plus 4 times 1/8, and so on. So we just have a sum of 1/2 basically, which continues forever. So we get an infinite expected value. So I guess we should pay any amount? Well, not really, because there's a 50-50 chance that we only get €1. So if we pay €1,000,000, that would be incredibly risky, because you can calculate the chance of even winning €100 is incredibly slim, very, 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 very slim. So we don't always only care about expectation, which is kind of what we stated in A5. Note that this paradox can actually be solved using utility functions, but it's actually not clear if there's no further problems there. I linked the Wikipedia article. This is a very, very famous paradox with many things to say about them. In general, all of the paradoxes listed today are, and I'm going to link the Wikipedia articles to all of them because I read all of them. They explain them very well. So, I've given the minimum requirements for constructing the situation which we have in Bayesian estimation theory, where we want to minimize our loss, which is the same as maximizing our utility. Sorry, our expected loss, which is the same as maximizing our expected utility. Okay, usually we have conditional expectation given x, but we've seen in the last video that's the same thing. So anyway, we've seen what kind of theory this approach is based on, which is something that's easily forgotten when mentioning this kind of theory, where I usually start with, that's how I started the last video. I start with, okay, we want to minimize expected loss. But the question is why, how, and what preconditions do we have? And as you've noticed, the preconditions, they're not perfect. There are situations where they don't hold. Now, given that I've listed a lot of paradoxes, which are very famous, and all of them have Wikipedia articles behind them, why do we still want to minimize the expected loss? Or in other words, why do we care about utility theory? And I want to start with the fact that it's perfectly valid to not like utility theory. There's nothing wrong with that. But it's still useful. It's useful in the sense that any model that we use cannot completely capture reality. Any model is restrictive. So just because I draw a perfect curve of a normal distribution, this really doesn't look like a normal distribution. I'm very bad at drawing. Just because I draw a perfect curve of a normal distribution doesn't mean that we actually have a normal distribution. Most often we have an approximation. We have some step function which kind of looks like a normal distribution. We have a differential which kind of estimates our equation. So even though our model doesn't completely capture reality, it is maybe not even sufficient, but it's necessary for us to talk about estimation theory. Because as I've noted, you can't really make much progress without talking about very elementary properties such as transitivity and comparability, which were A1 and A2, or even talking about maximizing, minimizing expectations and so on. It doesn't mean that you shouldn't forget the weaknesses of this theory. After all, this is what this video was about. But on the other hand, it doesn't mean that we're not going to continue using this model, because it's a very nice way to make progress in a very complicated setting. Okay, so this was a very different video from the other ones, because there was actually not not a whole lot of statistics behind it, but as I've noted, it's a little more on the background of why do we take this approach on statistics, Bayesian statistics, but also, I mean, classical statistics also operates with loss functions and expected loss and so on. And I'm really happy that this was also mentioned in great detail in the textbook. I highly recommend reading the textbook, by the way, because it's easily left out, even though it's very important. So I hope this was understandable. And yeah, see you next time, where we actually talk about the most difficult topic in Bayesian statistics, which is picking a prior distribution.